Nizar Habash is going to give a series of 3 talks. This is going to be on, essentially on Arabic subjects. And they will start tomorrow at 1 o'clock, I suppose. And it's my distinct pleasure to welcome our speaker, Eugene.
Fred, I'm crushed.
He's a person who needs no introduction, so he won't get it.
Just wait till I invite you to give a talk about it. Okay, I'm going to be talking about syntactic language modeling for machine translation and speech repair detection. This is joint work with Mark Johnson, Kevin Knight, Matt Leese, and Kenji Yamada. The talk comes in 4 parts. First, I'm going to give a quick review of statistical parsing and language modeling. Then I'm going to be talking about language modeling and the problem of speech repairs. Then I'm going to be talking about language modeling and machine translation. And then finally, some just off-the-wall speculation about where I see the grand future of artificial intelligence going, and NLP in particular. So parsing, of course, is the problem of taking a string, a sentence, and producing a phrase marker for it, a syntactic structure. And there are lots of reasons you might care about it. I care about it primarily because I think most of us agree that it is a first small step in the direction of the meaning of an utterance. Currently, essentially, all the best parsers these days are statistical in nature, and a lot of them are generative, and that's what I'm going to be talking about here, generative statistical parsing. And it works by trying to find the parse pi that is most probable given the sentence E. Okay, so we've got a sentence E, and we want to know what is the most likely parse for that sentence. And of course, we say most likely because in general there will be many possible parses for a given sentence. This is called ambiguity, and we want to find the one that is most plausible. And that, of course, simply by the definition of conditional probability is simply the probability of the parse and the sentence divided by the probability of the sentence. And of course, we can simply ignore the denominator there because that's constant over all the parses. The sentence doesn't change. And therefore, that denominator simply can be, if all you want to do is find the max, can be ignored. So what we want to find then is the probability of the parse and the sentence. That's what makes it generative. And that, in turn, can just be written as the probability of the parse, mainly because the parse, of course, goes all the way down and includes the actual yield, includes the actual words at the bottom of the tree structure or whatever it is you're creating. So that's what we want to find. Okay? And the way we do it in generative statistical parsing is by a top-down generative model that first starts out and says, well, we've got a sentence S. You can see it up there. And the first thing we want to know is what is the head of that sentence. So in this particular case, say we're going to guess that the sentence head is fell. What I'm describing, by the way, is not a real algorithm. I mean, well, it's semi-real. There are 2 problems to the parsing problem. One is the search problem, which is how you find a possible parse, and the other is the problem of evaluation. Once you're given a parse, how do you evaluate its probability? I am only describing the latter portion of this at the moment, and so that's why I said this isn't real. It's you give me a parse, and now I'm going to tell you how good it is. And the way I'm going to tell you is by essentially evaluating a sequence of probabilities, of which the first one is, what is the probability that the head of the entire sentence is fell, given, I just realized that my shirt collar is unbuttoned. And I won't be able to concentrate properly if I leave it that way. So what's the probability that the head of the sentence is fell, given that this is the root node of the sentence? And that will have a certain probability distribution. And then the next thing we guess is, well, what is the probability that fell is going to expand into a noun phrase and a verb phrase? That entire sentence headed by fell will expand into those. Notice, by the way, that we've already marked the verb phrase as having been headed by fell, and that's because the only way the entire sentence could have been headed by fell is if the verb phrase was headed by fell. And that will have a certain probability distribution. We'll multiply that probability in. And then once we've gotten to that part, we'll now say, okay, what's the head of the noun phrase? And that's prices. And that will be, we will get that probability according to some distribution that the probability of an NP headed by prices will be headed by prices, given that it's under an S headed by fell. And that will have a certain probability. And we'll multiply that in. And then we'll work on the verb phrase, and we'll say, okay, in this case, we already know that it's headed by fell. And the question is then, what's its expansion? And we'll say, guess that its expansion is that there's a past tense verb fell, and there's a noun phrase, and then, so on and so forth. Now, the point of all this is that once we multiply all those probabilities together, we get the probability of the entire sentence. And furthermore, the second point I want to make is that by conditioning the expansion rules and conditioning the probabilities that a certain word is going to appear in a certain place on previous words that we've actually seen, and not just on their parts of speech, we get a much greater degree of specificity in the probabilities. The probabilities are much, much sharper. So to give an example of that, consider the probability that a verb phrase expands into verb, noun phrase, noun phrase. Okay? And that probability is approximately 1 in 1,000 or 2 in 1,000, i.e. the probability that you've got a verb of the form, Jack gave the dog a bone. Noun phrase, noun phrase. Okay, overall it's about 1 in 1,000. On the other hand, if I tell you that the verb phrase is headed by said, that goes down to about 1 in, what is that? That's 100,000. Okay, i.e. it's much, much lower. In fact, it probably even should be lower than that, except we smooth these probabilities and thus can't afford to allow it to go to 0. Okay? Finally, if I tell you that, on the other hand, that the verb phrase is headed by give, now suddenly it goes up by a factor of 20 or 10. Now it's about almost 2 in 100, i.e. give is the kind of verb that takes 2 noun phrases. It's so-called ditransitive verbs. And thus, once I know that, the probability goes up. So the point is that these probabilities become much, much sharper. Here we had the unconditioned probability, and here we have 2 extremes, one where the verb is likely to take it and the other where it's not. This becomes also evident when we ask about what's the probability that a given word is going to appear in a given location. So we might say, well, what's the probability that the word is prices, given only that I know it's a plural noun phrase? Well, this is the Wall Street Journal, and that's where all this data comes from. And the answer is it's very likely. Prices is one of the all-time great plural nouns, and it's near, it's more, 1 out of every 100 plural nouns is prices in the Wall Street Journal. That's an amazing statistic. If you further specify that it's the head of a noun phrase, that doesn't change it very much, i.e. prices is used as the main noun as opposed to primarily as a modifier. If I tell you that it's not only the head of a noun phrase, but that it's immediately under an S, that means it's the subject. Probability doubles. So prices do things in the Wall Street Journal. Okay, they're subjects, they're not objects typically. If I further tell you that the S is headed by a past tense verb, it doubles again. And finally, if I tell you that what the prices were doing was falling, okay, that's really an astounding 15%.
Well, in certain years it's different.
That's right. Okay, so this was, you know, presumably prices rose is even higher, but, you know. So the point is that if you have knowledge about the domain, you can really use that knowledge to sort of enforce semi-semantic type constraints here. They're not really semantic, we're just dealing word to word, but you can sort of see that we're moving in that direction. And again, lexicalization helps sharpen these probabilities. Okay, having given you a very quick tour of syntactic parsing, now let's move on to speech recognition. Speech recognition is normally done using the noisy channel model, where we're interested in the probability of a string E given an acoustic signal A. And again, we use the noisy channel model to break that up into the probability of E, the probability of A given E, and divided by the probability of A. And again, we can just ignore the denominator because it stays constant. And so we get that. And this is typically, we refer to the pieces here as the acoustic model. That's the probability of A given E, and that sort of tells us how well the acoustic signal conforms to the string we're hypothesizing. And this is where, of course, I've been heading, the language model. The language model is the probability distribution, the so-called prior, on strings in the language. And what I'm essentially going to be talking about today is all sorts of ways in which, if you've got a good language model, you can use it to hammer all sorts of different nails. In the case of the so-called trigram language model, this is sort of the most familiar one, what we do is we estimate the probability of the entire string by the probability of each word given just the two previous words. Okay, so in particular, the probability of seeing dog after the and big is much, much higher than the probability of seeing dog after the and pig. And thus, if you had an acoustic model that wasn't too sure about the difference between big and pig, this ought to help you make the right decision, at least by the law of averages. On the other hand, consider an example like put the file in the folder versus put the file and the folder. Okay, this example has been cleverly designed so that all the trigram probabilities are high for both versions. Okay, so if you think about it, what are the trigrams? Put the file in versus the file and, both are likely. File in the, perfectly good. File and the, perfectly good, etc. So all the trigram probabilities look good, but there's a long distance dependency here that's being missed. Okay, and that long distance dependency is the fact that we know that put is a very unusual verb in English in that it essentially always requires a prepositional phrase after it. So if this is intended to be the end of the sentence here, the and version would be ungrammatical. Now, as I just illustrated, trigrams isn't going to notice this, but if you had a language model that was sensitive to syntax, it would notice this and thus would do better. Now, let's go back again to the generative statistical parsing. We said that the parser works by evaluating this probability. Okay? Well, if we, instead of taking the argmax, we do the sum over all possible parsers pi, what we actually get then is the probability of the string. And that, of course, is what we want for the language model. So essentially, you can take your statistical parser and instead of doing a max, just do a sum and you turn it into a language model. Okay? And that's what we're going to be doing essentially in the projects that we're describing here. So that takes us now to the two projects, of which the first one is language modeling and speech repairs. So first of all, what do I mean by speech repairs? Well, if you actually listen to recorded telephone conversations, what you find is a lot of the following. People start a sentence, they realize that they're not quite saying what they intended to say, they back up, and then finish the sentence off. So in this case we have, I want a ticket to Boston. So clearly what's going on here is the person intends or wants to say, I want a ticket to Boston. He or she started with need, fixes it up, and goes on. This occurs a lot, and this is known as one kind of speech disfluency, and in particular is known as a speech repair. Speech repairs are divided up into three parts. One is called the reparandum. This is the mistake portion of the problem. One is called the interregnum. That's the usually some filler pause, sometimes just nothing at all, that takes place between the reparandum and then the third part, which is the actual repair, which is what corrects the mistake. Now, there are many different ways you might want to think about handling this. I'm going to propose the simplest possible, which for 99% of the cases is good enough, and that is to say that what we really want in this sentence is just to get rid of this, and just leave the rest. There are occasional cases where that isn't good enough, but for 99% of the cases it is, and it's not time yet to worry about the 1%. Again, we're going to attack this problem. So the problem now is simply, given a string with good words and bad words, so every word will have a label. I'm a good word, I'm a repair, so I'm a bad word, I'm a good word, I'm a bad word, whatever. Remove all the bads and just keep the goods. So the way we're going to attack this labeling problem is, again, using a noisy channel model. We're going to say that we want to find the sentence E, which is most likely given the string with the repair markers, with the repairs in them. Okay? So we're given the long version, we want to produce the correct version. And the way we're going to do this, again, is using the noisy channel model. So we have a channel model using the probability of R given E, and of course we have the language model E. And so again, a good language model ought to help us. Now, at this point, that may seem just to be a mathematical trick. We've got a problem, we can use some math, divide it up into two problems, but is there any sense in which this really makes sense? And I claim it does. That these problems really are quite different. Why? Almost all natural language is recursive in the sense that it embeds structures inside structures recursively. Okay, so you start out with a noun phrase that breaks down into a noun and a subordinate clause, and that subordinate clause, like who ate the cookies, breaks down into a clause marker, the who, and then a sentence, ate the cookies. That in turn has structure, another noun phrase, another verb phrase, etc. And so it breaks down into this hierarchical fashion. Repairs, on the other hand, don't have any of this. Repairs look like copies of earlier text, pretty much without regard to their structure. So what do I mean by that? Well, again, look at that example. When you see I need wanta, you say, well, what is the structure of nida versus wanta? And the answer is, well, one is a rough copy of the other. That is, need corresponds to want, corresponds to Okay, so we've got this rough copy. It's not recursive. And in particular, what you can see is this has so-called cross-serial dependencies, i.e., when you have nice recursive structure, everything breaks down into this nice tree. You never have lines crossing each other. Okay? Well, here you do, and it's not just because I laid it out in a particular way. It's just that's the structure. It's so-called cross-serial. And This is very different from what we want with unrepaired strings of English. For that, we just want the nice recursive structure. So it really does make sense to break this down into two problems. One is the problem of finding these cross-serial things, and the other is, once you've gotten rid of them, make up a nice recursive structure for the rest. For the cross-serial stuff, we used a tree adjoining grammar. For those of you who don't know about tree adjoining grammars, they are a grammar that is just powerful enough to include all the context-free grammars and this kind of copying. Okay, so there's sort of a minimal extension to context-free that will allow this. And that's what we're going to be using for that part of it. I'm not going to concentrate on that because I'm interested in the language modeling aspects. Well, so we created this model, and we did some experiments. In the experiments, we used the Penn Treebank Switchboard 3 corpus. This is 1,300,000 words of transcribed telephone conversations. It's been tree-banked, annotated, and all the speech repairs have been marked, nicely enough. We took 2/3 of the corpus for training. 1/9 was used for development, in particular for setting the smoothing parameters, and 1/9 was used for testing, and we saved 1/9 for in case we had any other brilliant ideas. We tested 4 models where the only thing we did, well, shouldn't say that. One was a model that we had from a previous paper that that didn't use noisy channel. It used a boosting classifier to make the decisions. And then we did 3 noisy channel models, one using a bigram language model, one using a trigram language model, and one using a language model based on the syntactic parser. And of course, what we hope to show is that the better the language model gets, the better results you're going to get in the problem. And sure enough, that's going to prove to be the case. We measured the results using F measure on precision recall. So let C be the number of words correctly identified as edits. Let M be the number guessed as edits. N be the number of edits actually in the correct answer. Then precision is C divided by M. Recall is C divided by N. So precision is of the ones you guessed, how accurate were you? Recall is of the ones that you were trying to find, what percentage did you actually find? And F measure is the geometric mean between the two. Geometric mean? Harmonic mean. Thank you. I thought I was wrong, but I couldn't remember what was right. Yeah, so F measures harmonic mean between the two. Basically, if the two are the same, then the F measure is the same. If the two differ by a very small amount, it's sort of like the average. As the two differ by greater and greater amounts, it gets smaller and smaller with respect to the average. Is the way to think about it. So it penalizes you for widely disparate precision recall. Here are the results. So this is a previous paper where the F measure was 75.9. The bigram model was 75.6, so it wasn't as good as the previous results. The trigram model was somewhat better, and in particular was enough better to beat the previous results, but clearly it's the parsing language model that does the best. Okay? And the nice thing here is that there's every reason to believe that if we could plug in a still better language model, and thanks to some recent work that I'm very interested in by Fred and a student here, I think there's good reason to believe we can get significantly superior language models. This ought to go up with essentially no extra work. Basically just plug it in and you're going to get an improvement, and that's the sort of result I like, okay? The only trouble is you can't publish because they say, well, of course. Okay, now let's move on to the third part of the talk, where now we're going to be talking about language modeling used in machine translation. And this is some work I did with Kevin Knight. Again, we're going to use the noisy channel model. Anytime you talk about language modeling, you almost always talk about the noisy channel model. And here what we're interested in is we want to find the English or the target language sentence E, which is most probable given the foreign language sentence F. So the point here is that given say a sentence in French, there are many different possible English translations. So if the French sentence is le chien est rouge, for those of you who have red dogs, then the dog is red is a plausible translation. I own a piano is not very likely. And then there are presumably others in between. Although for that particular sentence, it's sort of hard to come up with one, but obviously for a much more complicated sentence, there would be many, many indeed. So we want to find the most probable translation, and that again will be the combination of our language model and our translation model. And there's the translation model, there's our language model, and now what I'm going to do is briefly describe both. So the first thing I need to discuss, however, before I go on to how we actually do this, and because this is going to come up later, is I now want to return very briefly to the search problem. Remember I said that parsing, there were two problems. One was, how do you find a particular parse for the sentence? And then the second problem was, how do you evaluate it once you've found it? And all I've been describing so far is the evaluation phase. Now I want to very briefly discuss how my parser does the search phase, because as we're going to see, this will come up later. The evaluation phase, you may remember, was top-down. We started at the top and we said, what's the probability of this word heading the entire sentence? What's the probability of now getting this expansion? What's the probability of getting this head here? What's the probability of the expansion? So we worked top-down. Almost all well, let me make a stronger statement. If you don't want to think too hard and you want to do efficient parsing, you want to do bottom-up. Okay? I mean, the only person who has not done that is Brian here. And he will tell you he had to think very hard. Okay? But if you do bottom-up, you don't have to think nearly that hard. It's really simple. Okay? Bottom-up parsing is very well understood. It's sort of very obvious, intuitive when someone tells you about it. So that's what everyone does. Okay? So now we've got this tension between bottom-up parsing, which is the easiest way to find parses, and the top-down evaluation, which is the best way to evaluate them. And so my parser essentially resolves this tension by splitting the problem into two pieces. One is a top-down algorithm for finding parses. This then goes in, once you have all the possible, or at least a huge fraction of the possible parses, it now does what a so-called pruning step. That is to say, it goes through all of the constituents that have been hypothesized and asks, well, how good are these really? And then the good ones it will pass on to the second phase, which is the top-down algorithm. This is the one that very intensively looks at all these probabilities and does the evaluation. Okay, and the pruning stage is done using this equation here. For those of you familiar with probabilistic context-free grammar parsing, this is a well-known equation. It basically says the probability of any constituent given the string is the outside probability of that constituent times the inside probability divided by the probability of the string. And if you don't know it, don't worry about it. the point is that once you have completed parsing, this is easy to compute, okay? Essentially, it's no extra time. However, you have to remember this is easy to compute only with respect to the grammar that you were using for the first phase of the grammar, which was not the complete model. It was just a simplified context-free version of that complete model. And thus, it's not going to be accurate for the second phase. So what you do is you set this sufficiently low, like 10 to the minus 4, 10 to the minus 5, and you keep anything that is reasonably plausible. This just gets rid of the real dross, okay? But 99.99% of this stuff is real dross. So that's quite okay. So that's the pruning stage. And so the parsing model then looks like this. We start with our bottom-up parser. We feed an English sentence into it. This produces a so-called packed parse forest. This is basically a structure that incorporates all the possible tree structures that could be assigned to this sentence, but in a packed representation because the actual number of tree structures grows exponentially, very badly exponentially. And so, but this doesn't. This just grows as the square. And so it's nice and compact. We then prune this and remove any constituent that is not sufficiently likely. Of those that remain, we then feed that into the second stage and get the most probable. And so that's how the parser works. Okay, put that now on the back burner. And now we're going to be talking about the translation model that this fitted into. And this is the Knight and Yamada model. And it works as follows. As before, we want to find the most probable English E given the foreign language sentence F. And we do that again by breaking it up into the language model and the translation model. Now what we're going to do, because we're interested in using syntax, is we're going to sum over all possible parses pi. So we're going to say we're basically going to take that top term and break it down by summing up. And that gives us the probability of E and the parse times the probability of the foreign given E and the parse. Okay? And then in the last equation, we're simply going to make two approximations. One is we're going to drop the sum. We're just going to ask for the argmax, okay, over both E and pi. And the other is we can ignore E in both these terms because the parse includes it, and same here, okay? So E doesn't add any new information. And so we get this equation. Well, this, of course, is going to be our syntactic language model. This now is a new form of the translation model where we ask about the probability of the foreign, not given the English, but given the parse of the English. Now, one way to think about machine translation systems is in terms of the MT triangle, as it's called. Here we have the foreign words. Here we have our target English words. In the so-called IBM statistical machine translation systems, essentially you go directly from the foreign words to the English words. Well, when I used to be in a field called artificial intelligence, we knew better than that. We knew that what you should actually do is you should go from the foreign words into some interlingua, and then once you had the interlingua, i.e. this sort of language of thought, you would then now take the interlingua and translate that back into English. And of course that was the right way, and we didn't deign to do anything as stupid as just do a word-to-word translation. Of course, that meant we didn't deign to do anything. But, you know, c'est la vie. Well, now what we're going to do is we're going to have a system which goes from the foreign words to an English parse, and then from the and that's our translation model, okay? And then from the English parse to the English words, and that's going to be modeled by our language model. So that's how the system looks. We are moving a little bit. This exaggerates, okay? This should actually be right down there, except you won't be able to see the difference, okay? So we're trying to move up, okay, gradually, the MT triangle. So the actual output from the translation model looks like this. It says, okay, here are possible phrases for pieces of the English. The numbers here actually correspond to which pieces of the French or foreign language component this thing models. Okay? And it then says, well, we can have a noun phrase and it can be translated into determiner, adjective, noun. And we also have a probability associated with it. In this case, these numbers are, of course, all just completely made up. So this 0.85 is intended to say this is the translation model probability. This is the probability of seeing the English or seeing the parse given the French. That's what the translation model probabilities do now. Similarly here, etc. So here's what our translation program looks like. We get in a foreign language sentence. It goes into the translation model. We then get out a packed parse for us, but now this packed parse for us is a packed parse for us in English. And it will contain those numbers like what we just saw of the probabilities of this piece of the English given the foreign language sentence. That goes into our language model, and then we get out an English sentence. Now, the reason I make this is because it's interesting now to put the two systems side by side. So on top here we have the translation model, and on the bottom we have the parsing language model. And you'll see there's a very high degree of symmetry here. In fact, it's so high that you can essentially combine the two without any real work at all, which means no more than about 4 weeks of programming. But I'm sure, as you know, that really isn't hardly any work at all. So what we're now going to do is say, well, look, in the completed system, what we're going to do is we're going to get a foreign language sentence, and that's going to go into the translation model. Okay? This piece goes away because we don't need it. We're not getting an English sentence into parse anymore. Okay? So there's our foreign language sentence that's coming in, goes into the translation model, and the stuff in the bottom now can be ignored because it's not a piece of the final system. Well, it goes into a packed parse for us, but of course that's exactly the same representation that we used here as our intermediate step. So we simply combine those two. Well, once we get that, now this said put it into a language model. Well, this is our language model right here. So what we now do is basically we say, well, there's our language model, and it produces our output in the form of a parse tree, and now the top can go away. So there's our system. And the reason I point this out is this is, I think, tremendously elegant. Okay? It just sort of fits all together very nicely, no fudging, almost. And there's your system. And sure enough, it sort of works. Well, what do I mean by that? Well, we did an experiment. We took the Knight Yamada Chinese-English translation system. It was trained on approximately a million Chinese-English sentence pairs from a parallel corpus. We tested it on 347 previously unseen sentences. 3 systems were tested. The so-called YC system, that's the one that we're evaluating here, that we care about here. The BT system, which was essentially an IBM Model 5 system, and the YT system, which was the Knight-Yamada system with a trigram model instead of the language model. We evaluated it both using IBM Blue scores and human acceptability judgments. In the latter case, we judged a sentence to either be correct grammatically or incorrect grammatically, and correct semantically or incorrect semantically. And that was the only judgment that the humans were asked to make. And here are the results. And those are the 3 systems we care about. YC is the one that we're rooting for, of course, and the other 2 are the comparison systems. And the big thing that I would like to push here is the number of correct sentences, both semantically and syntactically. 45 for the system with the syntactic language model compared to 31 and 26 for the other 2. Okay. Now, unfortunately, this was at some cost, and the cost was that, yes, we got more perfect, but we got fewer that were semantically correct, but not syntactically correct. And in fact, overall, you'll see we actually lost, if you take the addition of those 2, we lost 3 sentences that were semantically correct. So that's not statistically significant, and there are all sorts of reasons why this number should not be taken too seriously. In particular, there were 5 or 6 sentences that I couldn't parse at all, and the reason I couldn't parse them was because the original Knight-Yamada system was designed to use the Collins parser. And there are differences, in particular with punctuation, with how Collins handles punctuation versus how I handle punctuation. And the result is, since they produce Collins-style output, I couldn't handle it. Bye-bye 6 sentences. Okay? So there's lots of garbage like that. So I don't think that number, the fact that we lost 3 is not statistically significant, and is even less significant given the contingency, what's the word I'm looking for? I guess it's contingencies of the experiment. So, I shrug it off. But that 45 versus 31, obviously, that's big. Okay, we are definitely improving the syntax of the output by using a syntactic language model. Okay. Blue scores, if anything, went the wrong direction. Okay. It likes trigrams. Blue scores measure in terms of trigrams, so my personal philosophy is what this shows is that given a system based on trigrams and given a system not based on trigrams, Blue is going to prefer the system with trigrams. But hey, I lost here, so it's presumably sour grapes. But I suspect that just says something bad about Blue. Finally, if you like sentences that have great syntax but don't mean anything, okay, we've got the system for you. Okay? Here are some 2 brief outputs. One example is one where we just got it wrong, and I think partially this may just be because the syntax of the original sentence is sort of fishy. You can't say in English, Hu Yintao said. Okay, so my system wanted it to give it a direct object. Why breaking? Who knows? Okay, but it definitely felt uncomfortable without a direct object there. But here's the star of the lot. This is the one that I like to leave you with, okay? In fact, the central leadership is satisfied with Mr. Tung Chi Hua's administration, and you'll see the last one is pretty good. Central authorities, in fact, are satisfied with the policies of Mr. Tung Chi Hua, and the other two aren't, you know, even in the same ballpark, which is, of course, why I love this one. Okay, so finally, I've left myself enough time. Do I have an actual hour, or shall I?
Well, we have a telephone call.
I know. Okay.
That's the only.
Right, but I don't have to allow them time to ask me questions,
No,
right?
no.
Okay. Okay, so let's go back to the good old MT triangle, okay? And what we saw before was that what we were doing was we had a system that sort of went from there up to about here and then back down again. Okay. Well, people are now trying to work their way up. You know, I'd say right now we're maybe I'm working on a system that currently gets us maybe to there, and then over to here, and then down. But of course, eventually, what we'd really like, you know, the old people. You know, when I was in my AI stage, I wasn't wrong. I mean, it's not wrong to believe that there is an interlingua up there. I do still believe it. It was just not a good research strategy to worry too much about it. So, but, you know, we're now at the end of the talk. I'm not worried about what I do tomorrow morning or what I tell my graduate students to do. So we can speculate a little, and I speculate that this is, in fact, right. This is what we ought to be aiming for. And the only question is, what does that mean? And when you view it in a statistical framework. And the answer is fairly simple. From the viewpoint of a statistical framework, well, here's how we ought to be doing things. Instead of summing over parses or whatever, we ought to be summing over all possible interlingua interpretations of the string. Okay, and so that's what this represents. It says the way we are going to find the probability of E times the probability of F given E is by summing over all the interlingua representations, and we get that. We can then break that down into the probability of the interlingual representation times the probability of E given the interlingual representation. That's just from the first term of the equation, right? That's just a nice simple thing. And the second term, of course, remains pretty much the same. And then we can break it down now so that we say, well, once this term here and this is wrong, it should be there. Okay, move this bar over one. The probability of the foreign sentence given the interlingua and the English, to a first approximation, we can ignore the English. All we care about is the interlingua. Okay, and then we get this. And that, of course, is a very nice, very pretty, nice symmetrical equation. What it says is you've got the probability of the interlingua at the top, and then two translation components. Just what good old-fashioned AI told us about, except now expressed in a more modern statistical framework that says, well, one is we want to know what's the probability of the foreign given the interlingua, and the other is what's the probability of the English given the interlingua. And so that's really what our MT systems ought to look like. Well, furthermore, once you've gone that far, once you've now got this interlingua, what you really want, you don't just want a stinking interlingua, you want a world model. You don't just want a model of what people say, you want a model of the complete universe. What's going to happen next? And of course, if you had such a thing, not only would you handle speech, but you would also handle things like vision. Okay, so you know, I'm looking out in the world and I have a world model. My world model tells me that it's much more likely that I'm going to be standing in an auditorium filled with graduate students and professors than it is, say, with store mannequins dressed nicely in the outfit of college students and professors, okay? You know, so even if you, even on those very few occasions where none of you are moving, I very strongly believe, you know, thank you, that you're real people out there, and you're not penguins, and you're not any of the other things that might be there, okay? And the answer, why do I believe this? Well, I have a probability model over all possible states of the world, okay? Now, this sounds very grandiloquent, and you may say very implausible, but I see nothing implausible about it. In fact, to me, it seems absolutely necessary. How else could I manage? Okay? If when I walk out that door, I've got a probability model, even if I came in, say, from that door, I've got a probability model that says when I walk out that door, I'm going to be in a building and I'm not going to be on the street. How do I know that? It's obviously very important, because if I'm going to be on the street, I better be looking both ways before I walk out the door, and I'm damn well not going to, in fact, do that. And the reason is because I know what to expect. I've got this world model. And unless you had such a thing, it's very difficult to imagine how speech and language actually combine. At least I find it difficult to imagine. Okay, so that's really what we want. We want a probability distribution over all states of the world, and that's going to solve everything for us. Okay, but of course, the problem is AI complete. AI complete means that you can't solve it unless you've solved the entire AI problem. Of course, this is the entire AI problem to a first approximation. Okay? And, you know, it sort of looks impossible, but it's not impossible. It's merely, you know, tremendously difficult. Okay? So, and a lot of this subsumes normal things that have been the stock and trade of people in artificial intelligence for, I guess we're going on generations now, right? Such as something called the frame problem. The frame problem is when something changes in the world, most things in the world don't change because of it. Okay? So I move my arm. Yes, you know, maybe in a year there's going to be a thunderstorm in China that wasn't going to be there if I hadn't moved it, you know, but forget that. You know, that's just silliness. I mean, as far as my computation of the world is concerned, nothing in China is affected. In fact, nothing outside this room is affected. In fact, almost nothing changes. Okay, and that's what happens with most things, but some things do change. Okay, so if I go like that, well, I can feel a little draft on my cheek. So that did change. So this is called the frame problem. It's a very hard problem. It hasn't gone away, but it's now incorporated now into this overall goal, and it's now put into a statistical framework. On the other hand, taking it from the other point of view, this isn't just restating the old AI problem in new guise. There actually is a little bit of content to this claim because it suggests problems that otherwise you wouldn't look at. In particular, it suggests that looking at language modeling might not be a completely unreasonable thing to do. It's about as close as we can get these days, at least us in this community can get, to a world model. We don't know enough for the world model, but we do know enough for a language model. Or we're moving in that direction at least. And so it suggests that looking at language models might be more worthwhile than otherwise you might think, if you have this overall goal. Furthermore, it makes suggestions about how you might learn such models automatically. And of course, if you have certain kinds of language models, we all know, there are various statistical algorithms where these things could be learned from unlabeled data. The most obvious being the EM algorithm. And so it suggests that one thing we ought to be looking at is learning from unlabeled corpora. Well, of course, I don't have to tell most of you that. You know, this is a big topic. But it suggests that it gives you a reason, another reason for looking at this topic. Okay? And so, at any rate, that's what I've been doing in this talk. I've been working on language modeling. I've been showing you how it's useful in the small. I'm now trying to argue that it is on the path to the grand goal of artificial intelligence, however far along that may be. And thank you.
So in spite of being out of time completely, we'll allow 5 minutes of questions.
Okay.
If there are any questions, of course. Even the remarks will be answered.
Yeah.
I have a question about the last French and English, you said these are the two languages that you gave the example about, and then you use it for Chinese, right?
I was just talking in terms of French-English because I tend to think of that. Those were the first two languages that were ever handled using that model. So the prototypical languages for this are French and English. But in fact, I only showed you data for Chinese English.
Right. So my question has to do with this notion of divergences and how is that handled in this type of framework?
What do you mean by divergences?
Syntactic divergences, where certain things are expressed in more words or more in less words from one language to the other. Or
Right.
So is there like a mechanism in there that can handle that?
There are, okay, so let me talk about the system that I'm currently working on rather than this one, because I don't know enough of the details of how the Knight-Yamada system worked. I mean, roughly speaking, the answer is that in the original IBM models, there was this notion of a null word. Okay, so a word could just appear, and it was the translation of the null English word. That can sweep a lot of this stuff under the rug. Okay, because basically a lot of cases where the null word is something appears in the French given the null English word, and to some degree vice versa. Okay, you can have words in the English that map into nothing in the French or in the foreign language. So a lot of that can be handled through that mechanism. In the system that I'm currently working on with students, what we're trying to do is actually move up a level. So a lot of these null words are in fact syntactic nulls. They are basically pieces of syntax that don't go over to the other language. So Czech, for example, has comparatively few prepositions compared to English. Why? Because a lot of it is using case markings on the nouns rather than prepositions. So what happens? All these prepositions in English don't get mapped into the Czech. Well, another way of thinking about this is that in English, if you could map both representations up to a slightly higher level, where each noun phrase had a case/prepositional marker associated with it, and what you would then do is you would translate the case/preposition one to another, and then you would translate the nouns and adjectives one to another, and then at the end you would put that information together again. Okay? Again, Czech doesn't have the English way of combining modals with verbs to create extra tenses. Has been going. Okay, it's not something you would see in Czech. There are other basic tenses in Czech that English doesn't have. So again, what you want to do is you want to treat all those English auxiliary combinations as tense markers. And if you treat them as tense markers, then a lot of this stuff that doesn't map goes away. So ultimately, that's how I really want to handle this sort of problem.
So you have a coarser-grained level of representation.
A coarser-grained or a more, quote, I hate to use the word meaning because it's not nearly there, but moving up towards meaning, yes. Yeah.
One criticism I've heard from the speech community of the kind of syntactic language models you talk about is that speech engineers now have got access to lots of very powerful computers and huge amounts of data. Mm-hmm. And you could just argue that we can estimate 5, 6, 7 grams now.
Yeah, I know. I just saw the Franz Och's talk at the Corpora workshop.
What's the best response to that, Chris?
The best response is, for the moment, I'm just going to hide my head in the sand and pretend that Franz Och just isn't there. I would like to say, and I may actually believe, that you're never going to get really, really perfect translation through that. But if you had told me you could get the quality of translation he's already getting, I would have told you you couldn't get it that way. So I'm a bit hesitant. Worst comes to worst, I will justify this scientifically. Okay? I am a person who believes that the statistical approach we're describing is in fact what goes on in the mind. It is not the case, of course, that children sit down and read a million words of the Wall Street Journal, completely parsed before they start using syntax. But it is the case, I think, that they have something like a world model, something like a language model, and they learn this model automatically from unlabeled data. And it is statistical in nature. And so I believe that what I'm working is scientifically interesting. And worst comes to worst, I will justify it based on its scientific merit, if not its engineering merit. But I think we'll find some engineering merit too. The world is complicated. I'm not convinced that that 7 grams is all we're going to need.
But this is the last question. Go ahead.
So you just talked about child language acquisition, child world model acquisition. But certainly children have a lot of unlabeled data, but it's not in the form of text.
That's right.
So what do you think of the problem of trying to acquire a world model solely through text? Is it possible?
I don't know. I don't particularly care. It strikes me that the right way to do it is using both vision and text. I mean, that's the obvious thing to do. That's what I would ultimately care about. Whether it can be done just with text, who knows? It's not a pressing question for me.
We have to conclude because we have an important money grabbing, I hope, grabbing conversations with NSF. And Professor Charniak will stay here through the afternoon.
Oh, yes, I'll be here. Yeah, for those of you I told you otherwise, I will be staying for the entire day. So.
Okay, well.
Let's